Okay, so in the previous video, in this opening section of chapter 2, which as mentioned was really the opening section of all of calculus, that this entire calculus textbook, being that chapter 1 is just more of a pre-calculus. So in this opening section of chapter 2, we talked about how the foundation of all of calculus is the idea of a limit, the definition of the derivative and the integral, and even the infinite sequence and series concepts we learn in chapter 11. The foundation of all of this is the limit. So you can't have any kind of intuition of calculus without understanding what a limit is and how to evaluate a limit. And so in the opening section of chapter 2, we got a brief sense of the idea of what a limit is. And now in this second section of chapter 2, in this video, we're going to dive into the idea of the limit in more detail. Okay, but first, let's remind ourselves of the general idea of what we learned about limits in the opening section. Okay, so we were thinking about how we could determine the slope of a tangent line at a point on a curve. So we're given a curve, like in this example 1, we're given a curve, like the curve y equals x squared, okay? And then we're also given a point on that curve. So at x is equal to 1, then on the curve y is equal to x squared, y is also equal to 1. So at the point 1, 1 on the curve y is equal to x squared, what's the equation of the line that's tangent to y is equal to x squared at this point? That unique line, right? That's going to be one and only one line. Okay, well, to get the equation of this tangent line, it's really more about we need to find what the slope of this tangent line is. Because once we have the slope, well, then we have a point and a slope. That's all we need to write out the equation of a line, right? From algebra. So it's really more about, okay, how do we determine the slope of this tangent line? Okay, so to calculate the slope of a line, we need 2 points, right? One point has coordinates x1 and y1. The other point has coordinates x2 and y2. And so the slope is, we say it's m is y2 minus y1 divided by x2 minus x1. It's all simple stuff from algebra related to lines. Okay, but initially, we only have this 1 point here, the point that we're given on this curve. So what we do is we insert this second point. So we have point P, we're given point P, and what we do is we insert this second point Q with some arbitrary location on the function curve at x. So at some input x, if we input x into the function, the y value of this point is x squared, right? That's the coordinates of this point. This other point off point P, its coordinates are x, comma, x squared. Okay, now what we could do next is think about the slope of a line that goes through points P and Q. And now we can write a formula for the slope of this line, which we'll call MPQ. That would be, so, okay, y2 x squared minus y1, 1, over x2 minus x1. So x squared minus 1 over x minus 1. There's the slope of the line that goes through points P and Q. Okay, and this is called the slope of not the tangent line, but the secant line, because it intersects the curve at more than 1 point. Okay, and so now to get a feel for what the slope of the tangent line to the y equals x squared curve at point P must be, we can think about the idea of the x coordinate of point Q being closer and closer and closer to the x coordinate of point P, so 1. And that's what they do here in these two tables. So here in this first table, they let x get closer and closer and closer to 1 coming from above 1. And so for each of these values, they're plugging in these x values into the slope of the secant line formula and showing the result. And then they do a similar thing here in this table, but they're letting x get closer and closer to 1 coming from below 1. right? Because we could use this same logic here, and instead of putting point Q to the right of point P, we put Q to the left of point P, right? X can be anything we want, except for really just not X is equal to 1, because then we'd be dividing by 0. But X can be anywhere on this curve. Point Q can be anywhere on this curve. Okay, and so now if we analyze the results of this table, it looks as though as X it gets closer and closer to 1 coming from above, the resulting slope of the secant line is getting closer and closer to 2 coming from above 2. And as X gets closer and closer to 1 coming from below, the slope of the secant line is getting also closer and closer to 2, but coming from below 2. So it looks as if, it seems as though, we could potentially state that the slope of the actual tangent line, the literal slope of the actual exact slope of the tangent line itself, that one unique tangent line to the curve y is equal to x squared that goes through point P, the point 1, 1, is 2. Okay, and that's what there, so you have MPQ is the slope of the secant line, but just M is the slope of the actual tangent line, and it looks as if we can say that M is equal to 2, right? Okay, so, but we didn't make any official statements here. This is important to note. No official statements are being made yet. All we're saying is that it seems as though, if we had some hypothetical, very powerful calculator and could do arithmetic calculations to like 1,000 decimal places, then it seems to be the case that if we plugged into this MPQ equation values of x that were extremely close to 1, but just above 1, like 1.000, 1,000 zeros 1, and we calculated the result of this expression, we would get something like 2.000, 1,000 zeros 1. And then the same idea, if we plugged in to this extremely powerful calculator, something like 0.999, 1,000 nines, evaluated the MPQ result, we would get something like 1.999, 1,000 nines. Okay, so with that then, what we can say is that we can think about this sort of hypothetical abstract idea of a limit in that, so again, MPQ represents the slope of the secant line going through point P and point Q, and as we allow point Q to get closer and closer to point P, coming from the right side or the left side, we know that the resulting MPQ slope value is definitely getting closer and closer to the slope of the tangent line, to the curve at point P. But to think about what the actual value of the slope of the tangent line to the curve at point P is, the literal exact value, M, it's like we have to think about the hypothetical scenario of what happens to MPQ when P equals Q. But I'm saying hypothetical, though, because MPQ definitely doesn't exist when P is equal to Q, right? Because you can't divide by 0. But based on the analysis in these tables, and based on the assumption that if we did have some extremely powerful calculator and could do calculations, arithmetic calculations to thousands of decimal places, and could verify that from like an infinite perspective, this MPQ equation does indeed sandwich the value of 2 from above and below, then we could make a statement that hypothetically, if P were to sort of equal Q in this context, then the slope of the resulting line, which is the slope of the tangent line, would be equal to exactly 2, right? And so that's exactly what we do in this case. We go ahead and state that the exact slope of the tangent line, the unique tangent line, one and only tangent line to this curve y is equal to x squared at the point P is 1, 1, is M is equal to 2. Okay, but again, we haven't made any official statements yet. This is more of a thought exercise based on this like extremely powerful calculator assumption. Okay, but now we express this entire logical thought process using the term limit. We introduced this new term called the limit. The term limit is used to express this thought process we just went through. And the limit notation that's used is shown here. What we say is that the limit as q approaches p of the slope of the secant line MPQ is equal to the exact slope of the tangent line to the curve y is equal to x squared at point P, M. Or to express this mathematically, we could input the expression of x here for MPQ here and write this limit as, so the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to M or 2. Both of these limits are the same limit, right? They're making the same statement, just from different perspectives. Okay, and so now that we have the slope of the tangent line, we've got a point and a slope, and we could get the equation of the tangent line very easily, right? Using the point slope form of the equation of a line. Okay, and so before we get started with the next section, before we get started with section 2 and analyze this idea of a limit in more detail, there's two big characteristics of limits I want to point out, make clear to you, that we just talked about here in this example. Okay, first, it was important that we thought about a hypothetical, extremely powerful calculator that could plug in the input value with thousands of decimal places and evaluate the output with thousands of decimal places. Like, really, we could extend this to an even more powerful hypothetical calculator that could calculate to trillions of decimal places. And this calculator would be showing that coming from both above and below the input, the output value is being sandwiched. And it would show that with millions, trillions of decimal places as well. Okay, that's one of the most fundamental, important ideas of a limit. Okay, this idea of an input that's close to a value in like this, from this infinite perspective, and an output is being approached or sandwiched from this like infinite perspective. Okay, and second, also a very fundamental, important idea of a limit is that we were never concerned with what was happening exactly at the limit value. I mean, obviously, that is the overall main concern of the limit analysis itself, right? We were trying to analyze here find the equation of the tangent line that goes through the x is equal to 1 point. Okay, but like mathematically, from a calculation standpoint, going through all of the calculations here, evaluating this limit, we never thought about what was happening at the actual limit value. I mean, we couldn't think about the actual limit value because at the actual limit value in this case, we were dividing by 0, right? But to calculate the limit, to determine the limit, evaluate the limit, we had no concern whatsoever with what the function we were analyzing was doing at the actual limit value. What's happening at the actual limit value means nothing in terms of the calculation or evaluation of a limit. Okay, so let's keep those two very important primary characteristics of limits in mind going forward. Okay, so section 2, the limit of a function. Having seen in the preceding section how limits arise when we want to find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. All right, so we're going to move away from thinking about limits from the whole tangent line perspective and now just think about the idea of limits in general, from a general perspective. Okay, so let's investigate the behavior of the function f, defined by f of x is equal to x squared minus x plus 2 for values of x near 2. Okay, so we've got this polynomial function here, quadratic function, which we know graphs a parabola. And we also know that the domains of functions like this, of polynomials, you can input anything you want and you're going to get an output, any real number you want. All right, but now what we're wanting to think about is this function for values of the input x near 2. Okay, so the following table gives values of f of x for x close to 2 but not equal to 2. So once again, we're thinking about taking a calculator and plugging in values of x, values of the input that are closer and closer and closer to the limit value we're analyzing and evaluating the outputs. So they plug in values of x closer and closer and closer to 2 coming from below and coming from above. That's the input, and they calculate the corresponding output of the function. Okay, and what we see is it appears that as x approaches 2 from below, the output's going to be approaching 4 from below, and as x approaches 2 from above, the output's going to be approaching 4 from above. And based on our knowledge of polynomial functions and parabolas, this makes sense. We can even think about the graph. From a graphical perspective, this makes sense as well. And it says, in fact, it appears that we can make the values of f of x as close as we like to 4 by taking x sufficiently close to 2. Yeah, based on our knowledge of these types of functions, these polynomial functions, we know that if we had some extremely powerful calculator that could evaluate to millions of decimal places, and we plugged in 1.999 a million nines, we're going to get something that's not quite 4, but just barely below 4, 3.999 thousands, millions of nines, and then other digits. Same idea coming from above. Okay, so it says we express this by saying that the limit of the function f of x is equal to x squared minus x plus 2 as x approaches 2 is equal to 4, right? Because since we're sandwiching the value 4 with respect to the inputs coming from above and below 2, as we get extremely close to 2 coming from both above and below, it appears as though that the output value 4 is being sandwiched. We state this as, we express this as, we say the limit as x approaches 2, as the input of x approaches 2, of the function x squared minus x plus 2 is equal to 4. Okay? And so it says, in general, we use the following notation. So it says the intuitive definition of a limit. It's saying intuitive here because we're still not stating anything officially yet. This is still sort of a thought exercise. We're going to get into the more precise definition of the limit in a few sections. Okay, but now a little more formally, to talk about this a little more formally, suppose a function f of x is defined when x is near the number a, which means that the function is defined on some open interval that contains a, except possibly at a itself. Then we write the limit as x approaches a of f of x is equal to L. Okay, and we say, so we can make this statement if the statement is true if we can make the values of f of x arbitrarily close to L, as close to L as we like, by restricting x to be sufficiently close to a on either side of a, but not equal to a. Okay, so all we're doing here is we're just moving past these rough descriptions of what a limit is, and we're getting more and more official, more and more systematic with these definitions. Okay, but we're still defining this in a rough way. Again, we're going to do this more officially in a couple of sections. Okay, but what did they just say here? What constraints were put on our idea of what a limit is, the definition of what a limit is, what exactly it is? Okay, so with a limit right now, we're thinking about a limit associated with a single variable function. So a function f of x with a single input, and then a function is going to have a lone single output with respect to any given input, right? That's why it's called a function. With a function, you don't have multiple outputs that correspond to the same input. Okay, and so what this definition is saying here is that for there to be a limit of this function as the input approaches some specific value, a, right? So for the entire domain of the function, if you're asking what's the limit as the input value approaches a unique finite value, a, like 3 or minus 5, in order for that there to be some limit that does exist, and so it's some other finite value L, what they're saying is that, in a rough, unofficial way, is that you have to be able to go through this whole hypothetical calculation process that we talked about here. You have to be able to do this. You have to be able to think about some enormous calculator that you have, and you're plugging in values extremely close to A. So we're saying X is approaching A, like 2, extremely close to A, from above and below, and the function exists, right? Because you're getting output values. No matter how close you get to A, you can put these inputs into your huge calculator and you're going to get output values. And hypothetically, we can plug in values of X as close as we like to A from above and below, right? We can plug in 1.999, a trillion nines into the function, and we're going to get a value. We could plug in 2.000, a trillion zeros, 1, into the function, and we're going to get a value as close as we like, as long as we're not literally at A. We're not literally exactly at 2. Okay, and so that's what they're talking about here in terms of f of x needing to be defined when x is near the number A. Okay, but we can also notice, though, why does it say like this is an open interval that contains A? What's the significance of the term open here? Well, because if we come back to this table, the outer points that we start with, so here we started at, to approach 2 from below, we started at 1. To approach 2 from above, we started at 3. Those values are arbitrary. We could start wherever we want. The starting points coming from the outside don't matter, right? We could have started at 1.5. We could have started at -10. The starting points don't mean anything. It's really just about once you're starting to get really close to x is equal to 2. It's these regions that we're really analyzing. Not all of this. Okay, but now also notice how it says, except possibly at A itself. All right, it says this because if you noticed, once again, to go through this whole hypothetical calculation process, we had no need whatsoever to evaluate the function at A itself, right? So like whether or not the function was defined at A, undefined at A, or if it was defined at A, then what exactly was it defined to be? All of this had no association whatsoever on evaluating the limit 4, right? What was happening at the value, the input we were approaching, what the function is doing exactly at the value we were approaching had no bearing whatsoever on determining this 4 here. Okay, now we can also think about the meaning of the term near, so near the number A, from the perspective of how near. So like how near is near? Well, okay, technically, if you think about it, if we had some enormously powerful calculator, then as long as at least at some point, even if let's say that this function here we were analyzing as x approaches 2 wasn't defined or well defined until we got to like the millionth decimal place, until we got to like x is equal to 1.999, a million nines, then the function started to exist and we would get output values, and same idea coming from above, 2.000, a million zeros, 1. Then all of a sudden now we're getting values. And then from there we could, with our enormous calculator, we could keep going and do 1.999, a trillion nines and get a value, 2.00 trillion zeros and get a value, and verify that, okay, we are at this point sandwiching, that the output that's being sandwiched is 4 from below and above. Okay, well, then that's technically good enough to say that the limit exists and it's equal to 4, right? Okay, but like on the other hand, for example, if we think about, so let's say we have some function, let's say I'm defining this function to be, its domain is 2 and its range is 5. When x is equal to 2, y is equal to 5, f of x is equal to 5, and that's it. The function doesn't exist anywhere else. So if we graphed this function, we would get there's the function. I'll call this g of x, since we just used f of x. Okay, well, we can think about the idea of what is the limit as x approaches 2 of g of x. Okay, can we evaluate this limit? Does this limit make sense? Well, no, we can't, right? Why not? Okay, because g of x isn't defined near a or near 2, right? There's no way in this case for us to go through a hypothetical calculation process like this, because no matter how close x is to 2 from above or below, the function doesn't exist. We can't plug in 1.999 quintillion nines and get an output value to analyze what the function is approaching as x approaches 2 from either direction, right? We have to be able to see we're getting extremely close to the value we're approaching, and we want to be able to see, okay, what's the function doing? Well, it's not doing anything. It doesn't exist when x is near 2. Okay? So, roughly speaking, this says that the values of f of x as approach L as x approaches a. In other words, the values of f of x tend to get closer and closer to the number L as x gets closer and closer to the number a from either side of a, but x is not equal to a. We don't care what happens when x is equal to a. A more precise definition, we'll talk about an actual more official, precise definition of the limit in section 2.4. Right now, we're still just doing a thought exercise here. This was definitely more of a formal, systematic breakdown of the meaning of a limit, but this is still just like an intuitive thought exercise process to understand what limits mean. Okay, an alternative notation for the limit as x approaches a of f of x is equal to L is, so f of x approaches L as x approaches a. So an arrow like this can be used to state that something is approaching something. Okay. Notice the phrase, but x is not equal to a in the definition of the limit. This means that in finding the limit of f of x as x approaches a, we never consider what happens when x equals a. In fact, f of x need not even be defined when x equals a. The only thing that matters is how f is defined near a. Absolutely. Yes, the reason we're using a limit in most cases is because we're trying to determine what's something that's happening at the limit value, like in the case of the tangent line, right? We want to figure out the slope of the tangent line at this point A, but when it comes to actually doing the mathematics, evaluating limits, stating what a limit is, then what's happening at the limit value is completely meaningless. A limit is all about what some function is doing when that function is near the limit value we're approaching, the limit input value we're approaching. It's all about what the function is doing near that value. What the function is doing at that value means absolutely nothing. Like, for example, here, we've got these three functions. They're similar functions, and we're thinking about, okay, what's the limit? If these functions are f of x, what's the limit as x approaches a of f of x? Okay, well, in this case, you've got just a nice smooth function here. Nothing happens when x equals a, and so the limit is going to be L as x gets extremely close to a, as close as we want. We would see visually on like an enormous calculator, we would see the output value L being sandwiched, right? Now, if we come here, well, okay, they've changed it up, right? At x is equal to a, now we've got the function is still defined at x is equal to a. It's defined to be this value, but we don't have, it's not a smooth curve anymore, right? But again, who cares? The only thing that's changed coming from this limit to this limit is they've changed what the function is doing at the point A, which is completely meaningless. We could put a leprechaun, a unicorn here at A. It doesn't mean anything, because who cares what's happening here? If we could put this into a huge calculator and we were plugging in values extremely close to A from below and extremely close to A from above, we would be sandwiching the output value L. So that's the limit, right? And then here, what they do is they have this hole here, but now the function is not even defined at A. So before, if you input A into this function, you're going to get this value. If you input A into this function, you're going to get L. If you input A into this function, you're going to get undefined. So what? Who cares? Again, it doesn't matter if there's a leprechaun here at A, because we're never going to deal with the leprechaun. We're just going to say, look, we keep plugging in values extremely closer and closer and closer to A from below and above, and we're sandwiching L. So that's the limit. Okay? So now that we have a solid intuitive feel for what a limit is, let's now start thinking about how we would evaluate actual limits. So, okay, if we're given this limit, the limit as x approaches 1 of x minus 1 over x squared minus 1. Okay, so it tells us to guess the value of this limit. We're going to start off by, let's try and guess the value of this limit. Okay, well, what they do is they plug into a calculator x values that get closer and closer and closer to 1 from below into the function, and they do the same thing coming from above. And I mean, we could potentially think about as a trick for evaluating a limit, maybe we could plug in the actual limit value into the function. Maybe that could be useful, but in this case, it's not, because we can't divide by 0, right? But perhaps for like a polynomial function that has no holes in it, maybe it would be useful to just go ahead and try and plug in the actual value, the value we're approaching, into the function. Okay, but we can't do that here. Okay, but the results of this numerical analysis, this calculator analysis, suggest that. So, okay, it looks like we're sandwiching 0.5, 1/2 from below and above. It looks like if we had a really big calculator and we did 1 trillion 9s and 1 trillion 0s and a 1, we would still be, it would be a finer and finer sandwiching of 1/2. And so on the basis of this analysis here, we would guess that, okay, this limit is equal to 0.5. Okay, and so they plot the graph of this function, which is shown here. And what this is so you got x minus 1, and then you can factor x squared minus 1. So this is the graph of 1 over x plus 1, just with a hole at x is equal to 1, right? Okay, and so just looking at the graph, it looks as though that this guess is correct. Because yes, we can't plug in x is equal to 1, but we can plug in any other value of x we want, and there's no issue. And so based on this graph, we could get just like insanely, infinitesimally close to x is equal to 1 on either side, and we would be sandwiching the output value 0.5. Okay, and now they change up the question a little bit, and they say, okay, well, what if we wanted to find the limit as x approaches 1 of the function g of x, which is when x is not equal to 1, it's the same function we just worked with, but when x is equal to 1, the function is equal to 2. So what they're saying is that, so here, if we plugged in x is equal to 1 into this function, the function doesn't exist. But if we plugged in x is equal to 1 into this function, we get 2. So, okay, what's the limit of, as x approaches 1 of g of x? Well, it's still 1/2. Who cares what we did with the function at x is equal to 1? Again, we could have defined g of x when x is equal to 1 to be a unicorn. Doesn't mean anything as far as evaluating the limit. Okay? So now this next example, it says, estimate the value of the limit as t approaches 0 of this function of t. So we go through the same process. They're plugging in values of t coming from above and below 0 that get closer and closer to 0, and seeing what the calculator's outputting. And it looks like so in this case, we're not 0.1666, that's 1/6, but in this case, we're not going to be sandwiching 1/6 because we've got these t squared terms, right? So it's not like when t is equal to minus 0.01, you're approaching, the output is approaching 1/6 from below, and when t is equal to positive 0.01, the output is approaching 1/6 from above. No, for this function, because of t squared, this is an even function. So the f of t is equal to f of negative t. But still, that doesn't matter. It's not like we have to be sandwiching a value when the input is approaching a number from above and below. It's just we need to be definitively from coming from above and below, we're approaching something. And it looks like in this case that something we're approaching is 1/6. So we guess that this limit is equal to 1/6. Okay, but now what they show here is that we could think about continuing with the calculator and making the values of t closer and closer and closer to 0. And if we keep going, at some point the output is we get 0. And so they're asking the question, well maybe the limit is actually equal to 0, not 1/6. And they're saying no, the value of the limit is 1/6, and where this is coming from is just the numerical power of the calculator can't go to this many decimals. So this is a rounding error, right? So here they show the graphs of this f of t, and what they do is they zoom in closer and closer and closer, and this is what the actual graph of f of t looks like, right? And so you can see how it's not like the output has to be being sandwiched. You just need to be, from both sides, we're approaching the same value. We're approaching 1/6 from both sides, right? Okay, but as we zoom in closer and closer and closer, we can't even see the curvature anymore, but we keep zooming in. Now we get some sort of erratic behavior, but this has nothing to do with the actual function. This is the calculator can't resolve this, okay? So now this next example says, guess the value of the limit as x approaches 0 of sine of x over x. Okay, so the function sine of x over x is not defined when x is equal to 0. And they just start plugging in x values closer and closer to 0. And it looks as if sine of x over x is approaching 1. Okay, so it's not defined at x is equal to 0, but so what? Who cares? It looks like coming from both directions, we're getting closer and closer and closer and closer from both directions to 1, right? If you plugged in with a huge calculator, 0.000, a million zeros 1, positive 0.000, a million zeros 1, you would get something like 0.999, a million nines with some more digits. Then if you also plugged in minus 0.000, a million zeros 1, you would get it. So it wouldn't be 1.000, a million zeros 1. It would be, once again, 0.999, a million nines with some digits. But still, so what? You're still in both, coming from both directions, you're approaching 1. Okay, this next example says, investigate the limit as x approaches 0 of sine of pi over x. So, okay, again, this function is undefined at x is equal to 0. Now, evaluating the function for some small values of x, we get, so they do f of 1, f of 1/2, f of 1/3, 1/4, 0.1, 0.01, and they're getting 0 f of all of these values is equal to 0. And then if they kept going, f of 0.001, we're also getting 0. So we would, a guess would be that this limit is equal to 0. But it says this time our guess is wrong. It says, note that although f of 1 over n, where n is any integer, positive or negative integer, is equal to sine of n pi. So yeah, because if x is 1 over n, then you get sine of n pi, and that's going to be equal to 0 for any integer n, any positive or negative integer n. So that's true, but it is also true that f of x is equal to 1 for infinitely many values of x, such as x is equal to 2/5 or 2 over 101, as you let this get smaller and smaller and smaller, approaching 0. And so you can see this from the graph below. They're saying that because we were using these, we know that that trigonometric functions are periodic, right? And so it was the nature of these input values we were plugging in. We were tapping into the one portion of the periodicity that resulted in this function being equal to 0. But from another perspective, we could, as we get closer and as x gets closer and closer and closer to 0, we could keep getting 1 over and over and over again. And that's what's being shown here. As you get closer and closer and closer to 0 coming from either direction, sine of pi over x just continues to oscillate between 1 and -1. If we had an enormously powerful graphing software, we could zoom in as much as we want, and it would just continue to be oscillating. It doesn't exist at x is equal to 0, but near 0, it's just oscillating. So in that case, there is no limit here. Our guess is wrong in that the correct answer is there's no limit. The limit doesn't exist. Okay, so now this example 5 says, find the limit as x approaches 0 of x cubed plus cosine of 5x over 10,000. As before, we construct a table of values. And so, okay, as x gets, according to the calculator, as x is getting closer and closer to 0, it looks like we're just getting closer and closer to 0, right? So we might guess that this limit is equal to 0. But it says if we persevere with smaller values of x, so we keep going, it looks like, well, no, we're actually approaching a really small number that's close to 0. We're actually approaching 1 over 10,000, which we'll see later when we learn more systematic techniques for evaluating limits, that this limit is equal to 1 over 10,000. And so what they're trying to illustrate here is some of the pitfalls in guessing the value of a limit. It's easy to guess the wrong value of a limit if we use inappropriate values of x. But then also at the same time, it's difficult to know when to stop calculating values like they showed here. But even furthermore, sometimes the calculator can't even get that close as we might need, right? And then rounding errors come into play. And so what we're going to do in the next section, section 3 of this chapter, is we'll start to develop more foolproof methods, techniques for evaluating limits.